What if I told you that one of the most advanced telescopes ever built has discovered something in the deepest part of the universe that simply should not exist? Something so strange, so out of place, that it is forcing scientists to rethink everything they know about how the cosmos was born and how it evolved. The story begins with the Hubble Space Telescope, an instrument designed to look farther into space and further back in time than anything before it. But instead of just revealing the early universe as expected, Hubble uncovered something deeply unsettling at the very edge of the observable cosmos. Objects that, according to every known law of physics and cosmology, should not be there at all. And yet, they exist. This is not a minor irregularity or a small data error that can be brushed aside with a simple correction. This is a full-scale challenge to the foundation of modern cosmology, because if these observations are correct, then either our understanding of the early universe is seriously incomplete, or there are powerful cosmic processes at work that we have never even imagined. To understand why this is so important, we need to start with a simple but mind-bending idea. When we look into space, we are actually looking back in time. Light does not travel instantly. It moves at a fixed speed about 300,000 kilometers per second. That means everything we see in the sky is already in the past. When you look at the moon, you are seeing it as it was a little over a second ago. When you look at the sun, you are seeing it as it was about 8 minutes ago. And when you look at distant stars and galaxies, you are seeing them as they were thousands, millions, or even billions of years in the past. This turns the universe into a kind of time machine. The farther we look, the deeper into history we go. Now push this idea to its extreme. At the very edge of what we can observe, the so-called observable universe, we are seeing the cosmos in its earliest stages. We are not looking at the universe as it is today, but as it was billions of years ago, when galaxies were just beginning to form and stars were lighting up for the first time. This is where Hubble made its most famous and shocking discoveries. By pointing at seemingly empty patches of sky for incredibly long periods of time, sometimes hundreds of hours, Hubble revealed something astonishing. Those empty regions were not empty at all. They were filled with thousands of distant galaxies, each one a snapshot from the ancient universe. These deep-field images allowed scientists to look back more than 13 billion years into an era known as the Cosmic Dawn, the time when the first galaxies were just beginning to emerge. According to everything we understood, these early galaxies should have been small, chaotic, and underdeveloped. The universe was still young. There simply hadn't been enough time for complex structures to form. Galaxies, in theory, should have started as simple, messy clouds of gas and dark matter, slowly growing over billions of years into the large, organized systems we see today. But what Hubble revealed did not match that expectation. Instead of finding only primitive structures, astronomers began to see something unexpected. Some of these early galaxies appeared surprisingly large, unusually bright, and far more organized than they should have been at such an early stage of cosmic history. It was as if the universe had skipped several steps in its own evolution. And that raises a disturbing question. If these galaxies truly existed so early, how did they form so fast? Because according to our best models, they shouldn't have had enough time. And that is where the real mystery begins. To understand why these early galaxies are such a problem, we need to look at the standard model of cosmology, known as lambda cold dark matter, or Lambda CDM. This model is currently the best explanation we have for how the universe evolved from the Big Bang to today. It describes a universe that began in an extremely hot, dense, and almost perfectly uniform state. Over time, tiny fluctuations in density, barely noticeable variations in matter distribution began to grow. These fluctuations are visible today in the cosmic microwave background, the faint afterglow of the Big Bang, which shows differences so small they are measured in fractions of a percent. From these tiny irregularities, gravity slowly took over. Regions with slightly more matter began to attract even more matter, growing denser over time. This process eventually led to the formation of the first structures in the universe. But this process is slow. Gravity is powerful, but not instantaneous. It takes time for matter to collapse, heat up, and form stars and galaxies. According to the model, the first stars should have appeared a few 100 million years after the Big Bang. These early stars would then group together, forming small primitive galaxies. Over billions of years, these small systems would merge again and again, gradually building the massive galaxies we see today, including our own Milky Way. This is called hierarchical formation, small structures forming first, then merging into larger ones over time. It is a slow and steady cosmic construction process. But Hubble's observations do not fully match this picture. Instead of only finding small, immature galaxies in the early universe, astronomers discovered surprisingly large and well-formed systems at times when the universe was less than 1 billion years old. Some of these galaxies contain hundreds of billions of stars. That is comparable in size to modern galaxies like the Milky Way. But here is the problem. The Milky Way took billions of years to form. These ancient galaxies seem to have achieved similar sizes in a fraction of that time. According to Lambda CDM, this should not be possible. There simply was not enough time for gravity, star formation, and mergers to produce such massive structures. Even more confusing, some of these galaxies show clear organization, including disk shapes and early spiral patterns. These structures usually take billions of years to develop through stable rotation and density waves, and yet they appear in a universe that is still in its infancy. This creates a direct conflict between theory and observation. Either the model is missing something important, or the universe is capable of forming complex structures far faster than we ever thought possible. And the deeper astronomers looked, the stranger things became, because these were not isolated cases. They were part of a pattern, and that pattern was pointing towards something that should not be happening at all. One of the most important tools in understanding these distant galaxies is something called redshift. It is a way of measuring how far away an object is and how far back in time we are seeing it. As the universe expands, light traveling through space gets stretched. This stretching shifts the light toward the red end of the spectrum. The more distant the object, the greater the redshift and the further back in time we are observing it. Using this method, Hubble detected galaxies with extremely high redshifts, some reaching values of 9, 10, 11, and even higher. That means we are seeing them as they were when the universe was less than 500 million years old. At that stage, the universe should have been a very different place. According to theory, galaxies should have been small, faint, and still forming. Yet what astronomers found were galaxies that looked far more advanced than expected. Some of these early galaxies are not just large, they are massive. They contain hundreds of billions of stars, rivaling the size of modern galaxies. But forming something that large takes time, and the early universe simply should not have had enough of it. Even more surprising is their structure. Some of these galaxies already show signs of organized shapes, including disk formations and even spiral-like patterns. These structures require stable rotation and long-term gravitational evolution. In modern galaxies, spiral arms form through density waves that take billions of years to stabilize. Finding such structures in a universe that is less than 1 billion years old is deeply puzzling. Then there is the issue of supermassive black holes. At the center of most large galaxies today lies a supermassive black hole, containing millions or even billions of times the mass of our Sunday. These objects grow slowly over time by absorbing matter, but Hubble discovered evidence of extremely massive black holes existing very early in cosmic history. Some of them already contain billions of solar masses when the universe is still extremely young. This creates another problem. According to known physics, black holes cannot grow that fast under normal conditions. Even at the maximum theoretical growth rate, known as the Eddington limit, there simply is not enough time for them to reach such enormous sizes so quickly. And yet there they are. Finally, astronomers also found something even more unexpected: chemical maturity. Stars produce heavy elements like carbon, oxygen, and iron through nuclear fusion. When stars die, they spread these elements into space, enriching future generations of stars and galaxies. This means that early galaxies should contain mostly simple elements like hydrogen and helium. But instead, Hubble found galaxies that are already chemically enriched, containing significant amounts of heavier elements. This suggests multiple generations of star formation had already occurred, something that should require much more time than the universe had at that point. Every direction astronomers looked, the same problem kept appearing. The early universe looks too advanced, too evolved, and too structured for its age. And that is where the crisis truly begins to take shape. At this point, the tension between observation and theory becomes impossible to ignore. The Lambda CDM model has been incredibly successful in explaining many aspects of the universe. It describes the cosmic microwave background with remarkable precision, explains the large-scale structure of galaxies, and matches a wide range of observations across cosmology. But when it comes to the early formation of galaxies, something breaks down. The model predicts a slow, gradual buildup of structure over billions of years. Instead, we are seeing fully formed or highly advanced galaxies appearing far too early in cosmic history. This is not a small mismatch. It is a fundamental challenge. Scientists are now forced to consider several possibilities, none of them entirely satisfying. The first possibility is that the observations are wrong. Maybe distances have been miscalculated, or galaxy masses have been overestimated. But this idea is becoming less likely, because multiple independent observations using different methods are confirming the same results. The galaxies are real. Their distances are consistent. The problem cannot simply be explained away as measurement error. The second possibility is that our understanding of star formation in the early universe is incomplete. Perhaps stars form much more efficiently than we expect. Maybe early gas clouds were denser or cooler, allowing rapid collapse into stars. Some theories suggest that the first generation of stars may have been extremely massive and short-lived, rapidly enriching their surroundings and speeding up galaxy formation. But even this idea struggles to fully solve the problem. Too much efficiency creates new issues, such as intense radiation and stellar feedback that should actually slow down further formation. The third possibility involves dark matter, the invisible substance that shapes cosmic structure. If dark matter behaves differently than we assume, it could change the timing and speed of galaxy formation. However, alternative dark matter models often create new contradictions elsewhere in cosmology, making them difficult to fully accept. The fourth possibility is more radical: new physics. Perhaps our understanding of fundamental laws breaks down in the extreme conditions of the early universe. Maybe gravity, particle physics, or cosmic expansion behave differently than we assume. This idea is unsettling, but not impossible. Science has faced similar moments before, where unexpected observations forced entirely new frameworks. And now, a new instrument is about to push this crisis even further, because everything we thought we understood is about to be challenged again. When the James Webb Space Telescope was launched, it was designed to solve exactly these kinds of mysteries. Unlike Hubble, it observes the universe in infrared light, allowing it to see even farther back in time, closer to the very beginning of cosmic history. What it found did not calm the situation, it intensified it. James Webb began detecting galaxies at redshifts of 13, 14, and potentially even higher. That means we are observing galaxies as they existed only a few 100 million years after the Big Bang. And once again, the same pattern appeared. Some of these galaxies are far too massive for their age. Others appear unusually bright, structured, and chemically evolved. Instead of a simple early universe filled with small, primitive systems, we are seeing a surprisingly complex and active cosmos. One of the most striking examples is a galaxy known as JWST 130. It exists just over 300 million years after the Big Bang and already contains around 1 billion solar masses worth of stars. That level of structure and mass at such an early time is extremely difficult to explain under current models. James Webb has also detected early active galactic nuclei, supermassive black holes, feeding on surrounding matter. These objects suggest that black hole growth was already well underway almost immediately after the universe began. Even more surprising is the diversity of galaxies in the early universe. Instead of a uniform population of simple structures, we are seeing a wide variety of forms, including signs of rapid star formation and early chemical enrichment. The picture that is emerging is not one of a slow, steady cosmic evolution. Instead, it looks like the universe developed complexity far faster than expected. This has led scientists to explore new ideas. Some suggest extremely efficient early star formation. Others propose primordial black holes or exotic dark matter behavior. A few even suggest modifications to gravity itself. But none of these explanations fully resolve the issue without creating new problems elsewhere. And so, the tension continues to grow. Because the deeper we look into the early universe, the less simple it becomes. And that leads us to the final question. What does all of this actually mean? The truth is, we are standing at a very unusual moment in cosmology. For decades, the Lambda CDM model has successfully explained almost everything we have observed about the universe. It has been one of the most powerful scientific frameworks ever developed. But now, new observations are pushing it to its limits. Early galaxies appear too massive. Black holes appear too large. Chemical evolution appears too fast. And all of this is happening far earlier than our theories allow. So what are we left with? There are several possibilities. Maybe we are missing key details about how stars and galaxies formed in extreme early conditions. Maybe dark matter behaves in ways we have not yet discovered. Maybe black holes formed through unexpected mechanisms. Or maybe, just maybe, the fundamental laws we rely on need to be expanded. There is also a more unsettling possibility, that our observable universe may not be fully representative. Perhaps we are looking at a region with unusual properties, where structure formed faster than average. But even this idea challenges one of the core assumptions of cosmology, that the universe is broadly uniform on large scales. What makes this situation so important is not just the technical details, but what they represent. These anomalies are not isolated mistakes. They are consistent patterns appearing across different observations, instruments, and methods. And in science, when multiple lines of evidence begin to disagree with a strong and successful theory, it often signals the beginning of something much larger. History shows us this clearly. Unexpected deviations led to the discovery of relativity. Small inconsistencies in radiation led to quantum mechanics. Tiny irregularities in experiments revealed entirely new particles and forces. Revolutions in science rarely begin with dramatic announcements. They begin with something simple that does not fit. And right now, the early universe is not fitting. These impossible galaxies may be telling us something profound. not just about distant cosmic history, but about the limits of our current understanding. We may be standing at the edge of a major shift in cosmology, one that could reshape everything we know about the origin and evolution of the universe. And if that is true, then the question is no longer whether something is wrong. The real question is, what are we about to discover next? If you want more deep dives into cosmic mysteries like this, make sure to like the video, subscribe, and stay tuned because the universe is only getting stranger from here.